you.
All right. Lawrence, I'm sorry, I'm just going to say what the name is on the screen. So excuse me if I mispronounce your name. So Lawrence, go ahead.
Yeah, that's me. I'm Lawrence. I am here because I'm a geodata expert. I'm interested in topology in any way. And I'm now currently working since, I think, 3 months with BIM. So in that sense, it makes, yeah, that's why I'm interested.
Fantastic. Where are you located?
Right now I'm in Slovenia, but I'm from the Netherlands.
Fantastic. Last name Lima, Jao Cuero. Sorry, I'm not saying the name correctly. Yeah, go ahead.
Yeah, I was.
Could you speak up? We can hardly hear you.
Yeah, I have a lot of meetings around me because I have the kids with the pandemic. I have the kids at home. So my home office has been converted into an office school and everything. So it's a bit confusing. Yeah, but I'm very interested on Topologic. I've been following the forum quite a lot and even did these last sketch that caused some polemic. And well, I'm really interested in learning what you have to say and see. Oh, I'm an architect, of course, and see how can I adapt my practice to something that I feel is more in line with how I think.
Fantastic, thank you. Ryan, I can't hear. We can't hear you.
Now?
Yes.
Okay, cool. Hi guys, Ryan Schultz, architect in Madison, Wisconsin, in the States. I started opening design about 10 years ago. It's an architectural practice that looks to apply open source paradigm to the practice of architecture. And I've been interested in Topologic through Bruno's work. Also, I have background in Christopher Alexander's pattern language, and I see some applications with that as well with this program. So
great, good to have you. Lucas.
Microphone here.
Yes, we can hear you. Thank you.
Hello, I'm from Germany. I'm not an architect. I am electroplaner. That means building the electrical stuff into the housings. No programming experience, just following and very interested in what's the future of our jobs. Maybe the computer will do it on its own somehow.
Never. It will never do it on its own. But,
well, close to.
Yes.
At least for the electrical.
Yes,
that's not so complicated.
Welcome. I'm gonna let Bruno in. He's joining us, which is great. Miguel.
Hi, can you hear me?
Yes.
Hi, Basim. I was actually in your lecture the other day with Theo and Aberdeen course group. I don't know if
right, with Jonas, yes.
Yeah, and he mentioned that you were giving this lecture today, and I felt like I could learn a little bit more. I found it very interesting the first time, and I've been trying to use more Topologic in my Dynamo exercises for the coursework and so on. So yeah, that's basically it. But I'm an architect in Scotland as well, and in my practice we're trying to implement more the use of Dynamo. So that's why.
Great, welcome.
Thank you.
Yeah, today is going to be more perhaps I'll try to do something a little bit more hands-on, and then we can open it for discussion. And it's just very informal. We're just going to try to see, what I see is a lot of perhaps some misconceptions and some exaggeration. I mean, you give me too much credit, or you give Topologic too much credit sometimes, but also there's a lot of misconception about what it can and cannot do. And that's why I titled this Topologic Mythology, but maybe when you see it, you'll say, oh, is that it? Is that all there is to it? But we'll see. But we're going around the room introducing ourselves, and Bruno, you just joined us. Different Bruno then. Sorry, I thought it was Bruno Poster, but go ahead.
Hi everyone, I'm Bruno Perdigão. I'm an architect from Fortaleza, Brazil. And I have been following the discussion about Topologic. I guess I'm on this group that I don't understand very much, but I'm very interested. So and I would like to know how I can incorporate Topologic in my workflow. I work in a small studio, my own studio with another 3 friends, and I'm very curious. So I'm here to learn.
Fantastic, welcome. Okay, so let me tell you a little bit about where Topologic came from. If you have not seen some of the other presentations that we have done, tell you a little bit the story of its origins, and then why do people kind of get attracted to it, or what is so special about it? Why is it different than normal, BIM or normal modeling? And in reality, there is nothing, amazingly special about Topologic. What it has done is that it is the result of people like yourselves. I'm an architect. I studied for my undergraduate in Beirut, Lebanon, in the American University of Beirut, and then did my master's and PhD at the University of Michigan in Ann Arbor. And then in 2008 moved to Cardiff, to the UK, to Wales. And that's when I started working not on Topologic in particular, but on linking energy analysis to early design stages. So I wanted to do that. I wanted to offer that to my students, to kind of architects who are just starting to design, and they wanted to do energy analysis, and it looked overly complicated when you look at how you can do it in Revit and then Green Building Studio and all of these things. And I thought, my gosh, I mean, energy analysis uses very simple models. Why are we creating these very complex BIM models? At the same time, I was very much interested in parametric design and generative design and all of these new technologies. My area has been, and my PhD has been on computer-supported collaborative design and using parametric design, and wrote a book called Parametric Architecture for Parametric Design for Architecture. So it's been 7 years now. But I have been following somebody who is a pioneer in our area, and his name is Robert Aish. I don't know if you guys know Robert from practice. He was embedded in practice. Robert Aish is the person who invented generative components when he was at Bentley. So generative components was something that looked like a Grasshopper. You could do, link nodes together and do visual computing. But he was doing work on, in shipyards and shipbuilding, kind of like introducing CAD to that early 80s. So he's well known in that area. And then he left Bentley and went to Autodesk. And then at Autodesk, he went off radar for about 3 to 4 years. And he worked on a new computing language that is more amenable to architect, and he called it design script. So if you have ever used Dynamo, and don't worry if you haven't used Dynamo, Dynamo is built, or one of the scripting languages underneath Dynamo is called design script, and he is the inventor of that. Originally, design script worked with Autodesk and with AutoCAD in particular, and that's where I got introduced to it. And so I started using it and went to a couple of workshops, one in Cambridge, one in London, where he was there, and kind of I introduced myself. At that time, I was president of Acadia, and we got introduced. And in one of the workshops, he mentions, within 5 minutes only, he mentions that design script and the engine that they're using can do something called non-manifold topology. And very much like you at that time, in 2013, whatever, 8-9 years ago, I had no idea what is non-manifold topology. Why is an architect talking about non-manifold topology? I thought he was talking about like structural topology optimization. But basically, he was talking about the fact that some underlying engines can represent space and can take a space and do internal subdivisions and maintain that data structure, maintain that object. If you are using any kind of CAD program these days, it's very, very difficult if you want to, for example, include a line or a point floating in middle space, or it has wings or something like that, and maintain that without it complaining that it's an error and it needs to be closed. or a mesh that can leak water, for example, cannot hold water. All of these things are actually nowadays considered errors. They're considered like non-manifold errors. And you sometimes see it, like when you're 3D printing, it says your mesh is non-manifold. And that means that one edge is not shared by two surfaces. Maybe it's shared by three surfaces or by only one surface, and it's not closed correctly. There are certain types of engines like Open Cascade, which is the basis of FreeCAD, that can handle non-manifold edges absolutely fine. And if you look at the literature in the late 80s and early 90s, non-manifold topology, and in particular boundary representation, was supposed to be the way that BIM develops. BIM systems were supposed to use non-manifold topology. For some reason, very much like the VHS and beta kind of wars, the wrong standard won. So basically, manifold engines won the day, and therefore non-manifold topology went out of favor and nobody was using it. So now you have systems where you can aggregate objects. Fine, we can put cubes, let's say, and there is no way to ask a cube what's above you, what's below you, what's to your left, what's to your right. Like they're dumb. They don't know anything about their topology. And if you want topology, you have to either write your own software or use plugins or do ad hoc methods to get that topology recognized. So when Robert H. Was at Autodesk went and bought somebody's software that was created in a garage. His name is Ian Keogh. And he was inventing something called Dynamo, which was a clone of Grasshopper, which does nodes and visual programming and all of that. They bought Dynamo. They inserted design script as the scripting language of Dynamo. And in the process, started moving away from non-manifold topology and away from AutoCAD and all of that. Robert and Autodesk, I don't know exactly what happened, but basically they parted ways. So he went and became a visiting professor at the Bartlett at UCL in London. And at that time I had already done a research kind of project and connected it and wrote a paper about it, where I connected non-manifold topology to energy analysis, the software that I had before, to Energy Plus. And they pulled the rug from underneath me, basically. That's what Autodesk did. So I went to the Dynamo guys. I'm on good terms with them. I know them very well. And I pleaded with them in 2013 to bring non-manifold back, so that researchers like myself can use it. They were very nice to me, but basically they said there are licensing issues and there are technical issues that they couldn't bring it back. So basically Dynamo used to have it, or DesignScript used to have it, and it's actually still embedded in there. It's still hidden, but you cannot access it, and it's now gone. So facing like a bit of a brick wall with my research, I went to Robert H., who I know was interested in it, and he was the one who talked about it originally. And I said, Robert, how about you and I, do a research proposal to the Lever Home. We get it done, and forget Autodesk for now. We can implement it for Autodesk, but we'll do something that is open source, available to everybody. So from the beginning, our proposal to the Lever Home, if you read it, the promise is that it is platform agnostic and open source forever, free for everybody to use. It was part of my philosophy, kind of my interest. I did not want to do something that is commercial. And we are still pursuing that. This was, what, 7-8 years ago? We're still pursuing it. We got funded in 2016, finally, with 300,000 pounds, about $400,000 from the Lever Home. And we hired 2 research associates over 3 years, and we got it done. And it's still obviously ongoing as much as we can. Now we don't have funding for it, so it's our own kind of bootstrap, getting these resources to keep working on it. The most recent work that we have been doing with Theo and with Bruno is to bring it to Linux. So now we have an alpha software moving hopefully to beta soon. And within Sverchok, if you know Sverchok, looks like Grasshopper, and within Blender, we're putting it in Blender. It already works under FreeCAD, so again, it's available if anybody would like to try it out. If you are a brave soul, you can try it out. but it's not available as a workbench. You can just simply write Python scripts. So you have to type a lot in order to get it working. But if you know what you're doing, it's available under FreeCAD. But what I'm going to show today is an example of it running in Dynamo, and we will build a very simple semantic modeling example workflow, and I hope that will be interesting. Before I do that, we are joined by two more people who are good friends of mine, so I'll let them introduce themselves because everybody went around the room and introduced themselves. So go ahead, Theo. A couple of words about yourself.
Hi everyone, I'm an architect and a researcher. I work at Robert University. We'll be working with Vasim on this and other technologies. I'm happy to be here.
Good having you. Miguel, the other Miguel.
Hello, sorry to join so late. Just family logistics of these sites, of these times. But thanks for setting this up. As always, Wasim, you are overly generous. And just briefly, I'm a doctoral candidate. Actually working as a doctoral candidate, part-time enrolled in the University of Sevilla, but living in Stuttgart and working in Germany, and working 80% as BIM manager in an architectural office here in Germany.
Fantastic. All right, so let's just jump right into it. Feel always free to interrupt me, especially if I'm going too fast. But what I'm going to do, sorry about showing you all the windows here. I'm gonna, as I said, I'm gonna demo it in Dynamo, but it works very similarly in Grasshopper, and obviously we're moving it so that it works similarly in Blender's Fairchild.
Wasim, do you think I can interrupt you already?
Yes, of course.
So for me, what I struggle to understand first is what do you mean with topology exactly? What does this refer to in terms of geometry, and what is it?
Yeah, okay, that's absolutely fine. I will do it while I'm doing the demo. But basically, topology talks about how things are connected, so that your data is always connected. So when we are talking about the topology of a cube, as a simple example, you should know that, for example, the vertices of a cube form, the 8 corners. These are connected to edges. Mostly each vertex is connected to 3 edges. And these edges, 4 of these edges makes a face. And then the 6 faces make a solid, a cell, a cube. So when you are talking about geometry in these terms, when things are, they form parts in order to build a higher, more complicated structure, and they are interconnected, we are talking about topology. The geometry is obviously the physical kind of manifestation of that, how big these things in, where is the XYZ of that vertex, how long is the edge, what's the area of the surface, what is the volume of the cell. This is the geometry of it. Now I could change the geometry, I can inflate that cube, I can scale it, but the topology never changes. That vertex will always be connected to the same edges. These edges will always be connected to make a surface. So topology is what does not change when you are changing the geometry.
May I ask something?
Yes, please.
What if we do not make geometry, but we make electrical cables and plugs?
Yes. So that is what we call kind of pure topology.
Yes.
A graph, which is just simply made out of vertices and edges, not necessarily have any quantities to them, but the fact that a vertex, an edge connects 2 vertices, wherever they are and however that long is, that is called a graph, and that is pure topology. Topologic deals with graphs, absolutely, but deals with them also with their geometry. It brings the geometry because it's useful for us to have both geometry and topology linked together.
Okay.
But yes, absolutely, wires are a main part of topologic. And we call them wires, edges and wires and vertices.
May I add something, Wasim? Because
Yeah,
I think
of course. You don't have to ask for permission. Just jump in.
there's something you pointed out, but I think sometimes it's a little bit overseen or understated. Is that for me the core value for me in my personal research, the core value of Topologic is that topology, as you said, it works for any kind of geometry. Geometry has form. Geometry has a physical presence, but it can also be just a knowledge structure. But also the point for me is that parametric design has always been despised in its relation to the formal presence. Form is been too hard, too strong in relation to parametric design and to geometry. But the thing is that when we think topologically and in a topological basis, a topological structure, a set of operations, a construct, an artificial construct, will work for any geometry.
Yes.
And in that sense, it will need geometry indeed, but it will work, and the structure can be embedded and can be built for any geometry. And that makes form so to say worthless. So form,
I would call it
needed.
secondary. I mean, I would not, form would not be where, I mean, I think it would be secondary to the topological investigation, but it all depends on your interest in the design process. I mean, if you are interested in the topological connections, then the form becomes a derivative of these topological knowledge.
Exactly. So it's not anymore a main concern or a point of rejection towards parametric design, because if it works for any form, then the form is not the main objective or the main goal for any kind of designs, but the space. The work on topology for me is the ground that topos relate to space, not to form, not to objects, but to what we can inhabit and dwell. Yeah.
Exactly. One thing to also note in Topologic is that even though something that will look like a solid, let's say a cube, we do not make any kind of determination what is the material that is filling that boundary. That means a cell is a cell, it's a space. Now you can fill that space with a void, you can fill it with a solid, you can fill it with concrete, with plastic, with water, with oil, whatever you want. It is a region of space that is bounded by the faces that are interconnected. But it is really important, like for example, if I am designing something with a central courtyard, I do not leave the central courtyard empty. I actually can put a cell in there and just simply say, this is made out of air. So that's going to be a central courtyard. Because as a designer, as an architect, I want to know, is my dining room connected to the central courtyard? Well, if I never model the central courtyard, that topological relationship will never exist. There's nothing to connect to. So in a way, void or solid is really just a kind of an agreement, terminology, but for us, it doesn't make any difference. But anyway, let's go ahead, because looking at a blank screen maybe is sometimes not very useful. And I'm not going to sweat the details here because, I mean, obviously you need to know that Dynamo and how it works and all of that. But I'll try to explain what I'm doing. But once we get to the important stuff, I'll spend more time on that. But just accept that certain things are not going to be, you're not going to understand how this kind of things work. But that's not the point here in a way. But I'll just kind of like narrate what I'm doing. So I'm making a cube which is 10 units by 10 units by 10 units. If you are using metric, you can assume these are meters, or if you're using the American system, it's feet, doesn't matter. But I have a cube here. What I want to do is I want to do a 3 by 3 composition. So I'm going to do 3 cubes and 3 cubes in a grid. So that's how we do it in Dynamo. I'm going to just translate these. And if you know a better way to do it, please don't shout at me. I just do sometimes a very naive way of doing things. But it really doesn't matter. So I'm just going from 0 to 30 in the Y, and I'm going to make a cross-lacing so that they look like a grid. Now, it might look like a solid, but in fact, this is made out of several cubes, 3 by 3 grid. And as I said, that's not important how we got there, but you know, this is basically what we're doing. I just need to get the windows out of here. Just kind of get a good view of it. All right. And I'm going to flatten this list. Just make a list, and I'll show you what this list looks like. So it should have 9. Oh, why does it have 16? Sorry, I'm going from 0 to 30. I should go from 0 to 20. It should have 9 cubes, 9 cuboids. That's what it is. So now that I have these 9 cuboids, I can change them into topologic cells. So I can say topology by geometry. Now these are things that I have written, or the group, so excuse me, I should say the team has written. So this is all under topologic here. All of these things going from like a vertex, an edge, a face, a cell complex, etc. But topologic has only one entry point and one exit point, which is topology by geometry, meaning create a topology from a geometry, and then topology dot geometry without the word by, which means take a topology and translate it back into geometry so that I can see it onto the screen. By design, this is just now user interface issues, we decided that topology, or topologic, excuse me, should not draw anything to the screen until you ask it to, just to save you time. Because you are thinking systematically and you're thinking about topological relationships, most of the work that you are doing is about that, really not about the form, as Miguel has said. So we decided also not to draw anything to the screen. If you want to see something, if you want to see the geometry of it, you can do that. But mostly you are looking at the relationships. So once I have connected this geometry to topologic, I get 9 cells. So a cell is like a container of space. So once I do that, I usually go ahead and hide the original cubes, because right now I am in kind of my topologic world here. So let's start simple. Let's say I want to build a connected, so now these are 9 independent cells. They don't know about each other. In order for them to know about each other, you need to build a higher structure, which is called a cell complex. The word just simply means a group of cells, but they are interconnected. So I'm going to do a cell complex by cells. The word by is always like, you know, it's an agreement on how we do it. So cell complex by cells. So now I have a cell complex. Great. So you don't see it yet. So this cell complex is 9 by 9 grids. But let's assume I'm a kind of a structures guy, and I want to order the beams and columns that make that kind of cage. So let's go ahead and get the edges of this. So topology.edges. Okay, and let's go ahead and visualize them. So topology.geometry. Oh, sorry. And these are the edges. Now, what is so special about that? You look at that and say, well, I could have just drawn it in wireframe before. So what is so special? What is special about this is that there are no overlapping edges. So if you want to build this out of a wire of some sort, you want to get rebar, you want to get cables, you want to do anything, and you want to order these pieces that are 10 units long, you can count them. We can sit down here and count them. And Topologic will give you those unique items, never overlapping. So there are no overlapping faces, and there are no overlapping edges, and there are no overlapping vertices. Everything is unique, and everything is interconnected. So I can ask this vertex here to give me its edges, and it will give me those 3 edges. I can ask this edge to tell me which 2 faces it's part of, and it will give me this horizontal face and this vertical face. So everything is interconnected. So if we count them, do you want to go through that exercise? I don't know if you want to go through the exercise of counting the unique stuff, but you'll end up with 64, exactly 64 edges.
Could I ask something about this?
Yes, please.
What if somehow I made it in a different way and one of my cells is like 0.00001 centimeter off? What would happen then?
So if it is off within a tolerance,
yeah.
everything works within tolerance because we're using floating points. So it has a 0.0001 tolerance. But if it is off, and we get that a lot from dirty BIM models, as we call them.
Exactly.
It will not build it if it cannot build it. Within that, if it violates the tolerance, it will not build it, definitely. It will say, I cannot build a cell. In Blender, for example, now I'm experimenting with the default Suzanne monkey that they have the head. I don't know if you've seen it in Blender. If you use it as it is, it does not build a cell. But if just today, actually with Theo, I did a triangulation, and then I found something called mesh fix holes. And once I did that, Topologic built a cell for me. Before it was building a shell, because a shell is open. I should go through the nomenclature of Topologic. A vertex is a point, an edge connects two vertices. But remember, an edge doesn't have to be a straight line. Everybody thinks about an edge as a straight line. If I have a chain, a curve between 2 points, in Topologic, that's also an edge. It just has 2 points. But its geometry has many points. But the topology is 2 points, starting point and end point. You connect those into a wire. So a group of edges can make a wire. A closed wire can make a face. Again, the face doesn't have to be coplanar. It can be a NURB surface. The geometry of it doesn't matter. It's a face. A group of faces that are not closed are called a shell. So imagine like a cardboard shipping box, but open, not closed. That will be a shell. But if you close it, if it's watertight, it becomes a cell. And then if you take these cells and combine them face to face, they all share a face at least. They don't, they don't have to be complete. They can be like a link, but each one of them is at least linked to another one by a face. We call that a cell complex. And if you don't have any of those conditions, we call it a cluster, like just a group, of things. So you see them here on the left side. Okay, so we got the edges, perfect. So let's go ahead and get the faces. So topology dot faces, and again you can count them, and we can find out how many faces. But we have 42 little squares. Now, let's find out, let's do a simple operation. We need to find out the interior faces of this cell complex, right? So the interior faces are these interior walls, and we want to separate them from the exterior walls. So what is the rule for finding out? What do you find that is distinguishing between an interior wall and an exterior wall in this type of construction? What can I use to kind of test it?
They're connected to 2 cells.
Exactly. So the interiors are always connected to 2 cells. The exteriors are always connected to 1 cell. So I can test for that. So I can say topology.cells. And now we are climbing up the tree rather than climbing down the tree. Like I'm not taking a cell complex and say, give me the cells, or taking a cell, give me the faces. I'm taking a face and say, give me the cells that you are connected to. So it's a more advanced operation. So I get this list, a kind of a nested list. You'll notice that because I have a list of faces, 42 faces, and I will have a list of 42 of these things, so from 0 to 41. But some of them have only 1 element in them, 1 cell, and some of them have 2 elements in them. And that's obviously, let's say, this face index number 1, has 2 elements, has 2 cells. So obviously that's an interior one, and I need to extract it. So I can do a count. I can count these things. So I can do something like list.count. And I'm going to count this list. Now, if I count the list, it will tell me, okay, you have 42 things. But I don't want to count the top list. I want to count what's inside the list. So Dynamo allows me to do that. If you click this here, you say use levels. And I want to count at level 2, like the list within the list. So now I get a list of 1s and 2s. And I can put it next to this one like this, and match it. Like this one is an exterior, oops, sorry. This one is an interior, exterior, interior, etc., right? As a concept. Because this one has 1 cell, this has 2 cells. So now I can turn this into true and false. So I can do an equality test. So I can say, Okay, let's find out if this is equal to or equal to 2, the number 2. So tell me which ones are equal to 2. So now I have 42 of false or true. So I can use this to filter this list of faces. If it is false, don't include it. If it is true, do include it. So I can do something like filter by Boolean mask. And this is not topologic. This is all dynamo now. I mean, this is all, but as I said, what's important is not that I'm able to filter. What's important is that the face was able to answer the question for me. Are you bordering 1 cell or 2 cells? That's what's really essential about this. So I'll feed it the list of faces. And I get like an in list and an out list. The one that satisfies this condition of true, and the ones that are in the out do not. So I can take the ones that are in and visualize them. So I can say topology.geometry and visualize those. So those are the inner ones. Any questions on that? Did I lose people or are we okay still? Okay. And the out ones are the ones on the outside, including the top and the bottom, obviously. These are the exterior ones. And I can apply these things to everything else. But let's get to something a little bit more advanced, and I think Miguel would enjoy this one. So we're going to apply space program to this. So I'm going to put a living room, a bedroom, a kitchen, a dining room in all of these things. And now, obviously, this is not a real design or not even a good design, but let's just pretend. So I'm going to go do a dictionary by keys values. So what is that? Basically, a dictionary is nothing more than 2 coordinated lists. On the first column, you have the key, like you can call it name, first name, last name, salary, employee ID, whatever it is. And the second column is the actual value, you know, John, Smith, whatever, gender, all of that. So I will create this key and value. I can call them anything I want. So I'm going to invent something. I'm going to invent name as a key and maybe something called living room, just living, as a value. So I get a dictionary that has this key called name, and the value of that key is called living room. Simple enough. So I'm going to do it the naive way. I'm just going to copy this a few more times. And let's do a few things here. Sorry, I'm going to be a little bit inefficient about this. What else? I'll arrange them a little bit now. I'll put them all in a list. I'm a bit messy here. Okay. So let's call this dining. Let's call this kitchen. Let's call this bedroom. Let's call that bathroom. Let's do one more. Let's call it lobby, for example. Organized a little bit. We're architects after all. That's okay. I could arrange them if I wanted to. Are you with me so far? I just made dictionaries and gave them different space types. So I'm going to make one big list out of this, but I'm going to do something special about this list because this list should be the list of rooms that I have. Now I have here 1, 2, 3, 4, 5, 6 space types, but I have 9 spaces. So some of them will be doubled up. Obviously, I might have 2 bathrooms or 2 bedrooms. So I will do that. So I'm going to create 9 items. So from 0 to 8. And I will start, like, say, one living room here, one dining room, one kitchen, maybe 2 bedrooms. So I'll connect this to 2 items, maybe 2 bathrooms, 1 lobby, and let's give the living room like 2 spaces. Let's make it like, you know, some kind of like TV room and living room or whatever it is. So we have now a list of 9 dictionaries. Now the order is, I don't know what order I have done. So obviously if you are designing it, you would do it in a proper order and you assign it correctly. So I have a chat, so I'm gonna try to read it. Sir, must attend, call from my boss, try to, yeah, no worries. And okay, so we have those. So now I would like to assign those dictionaries to the cells of that cell complex, and Topologic allows you to do that. Okay, so I need to take those dictionaries and put them inside. So how do I do that? I need to find a point in space that is unique to the cell in order to tell it at that location, please put that dictionary. Okay, so how do we do this? A unique point in this construction that I have here is obviously the centroid. The centroid of every cell is unique to that cell. Otherwise, we have something called point inside. So you can get a point that is guaranteed to be inside that row. So we have the cell complex. So let's get the cells of the cell complex. So topology.cells. And this is the cell, sorry, no, this is the cell complex. So it should give us 9 cells, right? Those are the 9 cells of the cell complex, and those are interconnected. Let's get the centroid of those cells. So we get the centroid. So now we have 9 vertices. Those are unique. If I visualize them, I mean, let me go ahead and visualize them for you. Topology.geometry. Those would be the 9 centroids of the cells. If you see those little points there. I can use those as locators, or we call them selectors. So if I say something called set dictionaries here, I can give it the cell complex, the original cell complex. I can give it these vertices as selectors. So they are supposedly in the same order. Like if I do labels, you'll notice that they are in a certain order: 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the order. They're not in any kind of, so you need to know what order they are in, obviously, but for this purposes today, we don't care. But basically 0 is going to be a living room, and then 1 is going to be a dining room. That's what's going to happen. Sorry, let me do the chat one more time. So I have to go, we'll have to see video. No worries, we'll do, yeah. Right, so we put in the vertex as selectors, and we put in the dictionaries. And we also say that we want to apply it to only to cells, even though this is optional. So now we have a cell complex that has cells that have dictionaries. So it's no longer just geometry or just topology. It is geometry, topology, plus information. So how do we prove that? I know, for example, that cell 0, from what I can see here, because the first item is a living room, and I know that cell 0 is this corner. If I extract that cell and ask it for its dictionary, it should be a living room. Correct? So let's test that. So I'm going to say topology.cells here. So I got now back the 9 cells out of that cell complex after the dictionary has been assigned. Then I'm going to get the item at index, get item at index, and I'll give it a 0. So I got the first item, a topologic cell. Now I'm going to ask it for its dictionary, topology.dictionary. And it should say living room. if I'm not mistaken. There it is. Does that make sense? So these have now been embedded. So for example, let's take another one. Let's take number 4. So number 4, I can look at it here. Item number 4 comes in and it's a bedroom. Number 4. So let's go ahead and type in 4 here. And it's a bedroom. Make sense? So I can color code these now based on their room types. So for example, I can say, let me create 1, 2, 3, 4, 5, 6. So let me go ahead and create 6 colors. Six. All right. And then I can say topology.geometry from those cells and hide that. Okay. Now I will do it. I will do it with a bit of a Python script. And this will be the last thing. I won't keep you any longer than this because this gets to be a bit much. But basically, what I'm going to say is I'm going to feed it the cells. So let's go ahead. Cells is equal to in0, right? And then I can say, let me see, because I have it here from my cheat sheet here. I can say that I can do an index. Let's see here. Yeah, I can say an index equals. So the living room is 0. Let's say the kitchen is 1. Bedroom. Bedroom is 3, etc., etc., etc. I'm not gonna, you know what? I'm not gonna waste your time with this. It's gonna take a while to write this up. I think it's getting late in the day. Let me not do that, and just let me open a new one, the one that I had before. So I will not save that, and let me just open the one that I had before. Just show you the end result of it. Because the details really doesn't matter, and I can show you. I can share that definition with you. No worries, Ryan. Thanks. But you see it here. This is the same thing as we have before, where you're able to color code them based on what they are, but also you can derive the walls that are between certain spaces. So in this definition, I'm saying I want the walls that are between the 2 bedrooms. So that gives you walls that are between 2 bedrooms, or between a bedroom and a bathroom, excuse me, as it says here. So if I want to see the walls between the living room and the kitchen, if I want that, there are no walls between the living room and the kitchen. Okay, so we'll do between the living room and the lobby. No, there's nothing between the living room and the lobby. Hold on. Let's try living room and dining. What is going on here? Doesn't seem to be wanting to work very well. Let me try again. Bedroom, bedroom. I think I broke it. It was working, but I don't know why. Okay, bathroom and bedrooms worked. Maybe bedroom and lobby. It doesn't want to work on the other ones. I don't know why. Not sure. I must have like messed with it and didn't work. But the idea is that it can give you the walls that separate cells that have a certain dictionary. I mean, that's the whole idea. I know it does work, but somehow I must have messed with it. And it's color coding them based on the space type. So you can change, for example, if I make, so the living room, for example, here is not there. So if I assign it to a different item, you'll see that the light green, because you see how there are 1, 2, 3, 4, 5. There are now 5 light green cells that are all living rooms. These are the ones right here. And if I assign more kitchens, for example, you'll notice that the kitchen starts taking over. So when you see Miguel on the website kind of talking about informational modeling, is that this geometry really doesn't matter. It could be any kind of geometry. What he is manipulating, what I'm manipulating, is basically the information that, you know, sort of like, what is the meaning of these spaces? Are they kitchens? Are they living rooms? Are they public? Are they private? And all of that. But I'm going to stop here and maybe take a few final questions before I let you go.
May I? Hello? Yeah. So topology is an engine which behind it has a kind of database storing the dictionaries, storing the edges, connections.
Yes.
And also the asking mechanism for those informations. So it's a database or a graph base, or what is behind, and this is topological. That would what we could use for FreeCAD or use for Blender or use for whatever else.
Correct. It is both the database connectivity, but also it is a geometric engine, a very, very capable Boolean operations, geometric B-wraps, all that. So anything that FreeCAD can do, because FreeCAD is based on the same engine, it's called Open Cascade or OCT. So Topologic is not just a database management system. It's really not that. It is
coupled with the geometry.
It's a 3D CAD kernel, as they call it. But we layered on top of it the ability to handle dictionaries, embed dictionaries in geometries, extract them, and manipulate them.
Okay.
Yeah. And as well as we build graphs, like graph theory is built into it. Mm-hmm. Like I can get the dual graph of this one. I can do traveling salesman. I can do shortest distance. I can ask whether the graph is cyclic or not. I can find whether there are islands, like find the graph cycles. Anything that you can do with graph theory, you can do here because you have the graph structure.
Can I have holes in faces? Can I? That's yes. Topologic. And when I have two faces which don't share any vertices, do they still get recognized as one face?
Yes.
If they share part of the face. Yeah.
Yeah. I mean, you can have holes. I mean, it's a boundary representation. So anything you can model will be represented as best as it could. So you can have shells. You can have shells with holes. But not only that, we have the idea of aperture. So if you want to do a door inside or a window inside those faces, you can do that by overlaying another face on top of it. So faces can also, or any object, any topology can have contents. can have like other things in it, other faces or other cells in it. Detached, not connected. Yeah.
So if I have, for example, two cubes that are touching with one face, but the vertices don't match, it will still recognize the faces as touching,
Correct.
even though the vertices are not in the same place.
Yes. Yeah, absolutely. Absolutely.
And then I have one more question. You said that you're working on Sverchok in Linux, but it's all Python, right? So it means it should work immediately in Sverchok for Windows or not?
No, unfortunately, not yet. We're working very, very hard on that. We're having technical issues with that. So in order to bring the C++, Topologic is written in C++, in order to bring it to Python, because that's what we did, we brought it to Python. It was much easier to bring it to Python on Linux using something called CPPYY. It's another piece of software that translates C++ into Python. It does exist for Windows, but we're having a lot of technical hurdles making it available for Python for Windows. So Python for Linux is straightforward, and we have it. You can download it from the GitHub. We have it available, and you can run it on Linux. For Windows, we can run it under, right now we can run it under Dynamo and Grasshopper, but we're hoping to get it for Sverchok. I mean, once we have Python for Windows, everything is available. We can put it in Blender, FreeCAD for Windows, and Sverchok for Windows.
I just thought that when it's written or in C++ ported to Python, then it doesn't matter if it runs on Python Windows or Python Linux. But yeah, apparently that's.
I would love for somebody to help me with this. We are looking for Python C++ experts who know how to compile it and can get it running on Windows. If you know anybody, just put them in touch with me for sure. All right. If there are no other questions, guys, we'll continue the discussion back there. On OS Arch, but thank you for listening in and have a good weekend, everyone.
Thank you very much.
Thank you.
That was great.
Thank you.
Thanks. Bye-bye.
See you.
Bye.